In industrial and instrumentation applications, systems often have to transmit data over very long distances in extremely harsh environments. The RS-485 bus standard is one of the most widely used physical layer bus standards for these applications, but there are 4 common problems you'll need to overcome in your network design. So let's look at the first problem. How long can you make your cable, and what data rate can you use? RS-485 can communicate over long distances by using differential communication lines. This requires a dedicated pair of signal lines, A and B, to exchange information where the voltage on one line equals the inverse of the voltage on the other line. A RS-485 receiver connected onto the bus will output a 1 when line A is 200 mV greater than B. Similarly, the receiver will output a 0 when line B is 200 mV greater than A. By using differential communications as specified by RS-485, typical examples of data rate and cable length combinations vary from 90 kilobits per second at 4,000 feet to 10 megabits per second at 15 feet. So let's move on to the second problem. How many devices can I connect onto my network? The input impedance of an RS-485 receiver is specified as larger than or equal to 12 kilo ohms or 1 unit load. This allows up to 32 receivers to be connected onto the bus. Every receiver that you add onto the bus will add an additional load to the driver. You will be able to increase the number of nodes you can connect onto the bus up to 256 by changing the load of the receiver to 1/8 of a unit load. Let's move on and look now at the third problem. How can you deal with the bus idle condition? The bus idle condition can occur in terminated multipoint applications when the transceivers connected on the bus are all in receive mode simultaneously. This will cause the differential voltage on the bus to be close to 0 volts, at which the receiver output is actually undefined. Random data will appear on the UART and can cause erroneous system operation. The bus idle condition can be solved by placing a combination of pull-up and pull-down resistors at one position on the bus. This is often referred to as short-circuit failsafe. Newer RS-485 transceivers have an improved feature that include true failsafe receiver inputs. This eliminates the need for pull-up and pull-down resistors. If a transceiver is specified to have a true failsafe feature, it means that an offset has been added to the differential input threshold voltage. If all transceivers connected to the bus have true failsafe, the receiver outputs will always be defined. Let's move on now and look at the last and most severe problem. How can you protect your network against harsh EMC events? Lightning strikes, power source fluctuations, inductive switching, and electrostatic discharge can cause damage to RS-485 transceivers by generating large transient voltages. Protecting RS-485 networks against the harsh EMC environments in your system often requires several design iterations. Isolation can be used as protection by preventing the flow of current while still being able to transmit data. The ADM2587E is a signal and power isolated RS-485 transceiver in a single package that will provide an isolation barrier to protect against these harsh EMC events. A second way of protecting your RS-485 network from EMC is by adding a shunting circuit on the A and B lines. Check out circuit node CN0313 for more information. Thank you for watching. For more information on RS-485 and implementing your next RS-485 circuit, please visit our website at analog.com/RS-485.